we're now going to talk about surface integrals and do what we can to connect it to what we have already seen. So specifically, we had seen that if you have capital S is a surface parameterized by a vector function, so r of u comma v is equal to angle bracket x of u comma v, then comma y of u comma v, then comma z of u comma v. For u comma v being an element of or a member of capital D, this capital D is the parameter domain. That's what we call it, parameter domain. Then the area of the surface S is given by the following double integral. It's the double integral over the parameter domain of the magnitude of the cross product of r sub u times r sub v, close magnitude here, dA, where this dA could either be du dv or dv du. So that's what we had already done. And now what we want to do is we want to connect, basically think of computing the area in this way as a warm-up, and we now want the area of a surface to end up as a special case of a more general thing, being integral over S, the surface itself, instead of D here, just the surface itself, of the function 1 d capital S. By putting a 1 here, this really is a function, so we mean like f of x comma y comma z is just the constant function, just always gives the value 1. And we want this to end up translating eventually to be this integral over d, this integral that we had up there. Yeah, so we really want to have here integral of ru cross product rv, take the magnitude of that dA. That's the connection we're off to try to make. Now, recall, we're going to connect this back to line integrals as best as we can. If capital C is parameterized, so look at how already we're trying to make some similarities here. If capital C is parameterized by x of t, y of t, and t going from a to b, then we had the integral over c of, we're not going to have room there, integral over c of f of x comma y ds, that this equaled, to implement and actually compute, we had an integral with respect to t. So it's integral t going from a to b of f of x of t comma y of t, and then the ds gets replaced with this radical dt. Okay, so inside the radical is a dx over dt squared plus a dy over dt squared. Now, we're just going to take what we have here and restate it. So same thing, just with slightly different notation, and it's going to help us connect things better. So if capital C is parameterized by, we're just going to repackage the parameterization. Instead of having an x of t and a y of t, we're really just going to restate this as a vector function. That's all. So parameterized as r of t equals, an angle bracket, x of t comma y of t for t between a and b. Then this same line integral, integral over c of f of x comma y ds, we're really just going to say this is integral from a to b of We haven't written it this way, not for us in a line integral over a scalar field or a scalar function, but we're going to now do this. We're going to write f of vector r of t times the magnitude of r prime of t dt. So let's just take a look with a little bit of color here that this right there actually is the same as this. I mean, if you really took this, if you took this vector function right here and you took the derivative and then you took the magnitude, that really ends up being the same. Now, we've so far avoided saying it this way. We have avoided so far writing it this way because it might have confused people in talking about the line integral of a vector field. So just to not, there was no need earlier to try to connect these issues, but right now this will be helpful. The point is we have, so ds, that's actually, this right here or this right there is actually equal to root, so copying from the first implementation of this integral, dx over dt squared plus dy over dt squared, okay, all in the radical dt, or another way now that we have this is the magnitude of r prime of t dt. So all these things that are underlined in red are the same. They, of course, look a little different, but they're actually all equal. Now, what we're going to do is go back to this surface parameterized here. In fact, let's just restate this. Okay, so this was for the area. What we're going to try to do is make an analog to this. So if you have a surface S, and S is parameterized by a vector function, so I'm trying to make this sound as much like what we have right here as possible. Okay, so parameterized by an r of u comma v equals angle bracket x of u comma v, y of u comma v, z of u comma v. Just for, how about u comma v in parameter domain? So that's as close as possible to what's being stated right there. Okay, these two boxes are meant to sound as similar as possible. It's just for a curve or a line, you only need one parameter t, and for a surface, you're going to need two parameters u and v. Now, let's get a line that looks as similar to this as possible. Okay, and it will look like this. So then we'll have, the double integral over S, meant to copy like single integral over capital C, of f of x comma y comma z d capital S is equal to the double integral over d of f of r of u comma v times the magnitude of the cross product of r differentiated with respect to u and then r partially differentiated with respect to v dA. So this is super important. We're going to, of course, practice this a lot, but before practicing, let's just make as many of the connections as possible. So first of all, let's state this. So d capital S is magnitude of r sub u cross product r sub v, close the cross product dA. Now, we've already underlined some things in red, so how about let's underline here in blue. Okay, so ds is meant to be like d little s. Now, it's different, right? So that's why just a new color. So that's here, and so just like above we had ds replaced with that, now what we have is we have d capital S replaced with this. A couple other things are in order to mention. So first of all, let's point out that right here, this double integral over d, this is meant to be like earlier we had the integral over the integral t going from a to b. So when it was just a single variable, you just need to know where t starts and t ends. And now that there's two variables for the parameterization, u and v, it's just more complicated. So there's just a shape d instead. Okay. This next part here, this f of r of u comma v, this is meant to be like earlier this f of r of t. So it's meant to be as similar as possible, f of r of t. We're just pointing out the similarities. And then this next part right in here, just the magnitude part, that's meant to be like what we had right here. Okay, so this is meant to be like magnitude of r prime of t. So inside the magnitude, what are we taking the magnitude of? It's a derivative of r, and that's about as similar as we can get here. These are now partial derivatives of r, both partial derivatives and a cross product. Okay, so think of the prime here that you see. Think of the prime. Think of this like, sort of like the r sub u. You know, like the subscript, the fact that we're doing a partial derivative. And then finally the dA that's right here. Okay, this is like the fact that earlier we had a dt. So dt, so yeah, the dA is like having a dt. Okay, it's about as similar as possible, what the analogy is. What dA is going to actually become, so dA will actually become, you know, du dv, or will become dv du. Okay, so since this is a video, I know that maybe this is a little messy and I kept trying to circle and then erase, but really let's now do this. I'm going to kind of mess things up a little bit in doing this, is that this part is meant to be like this part is meant to be like that, this part is meant to be like this, and this part is meant to be like that. Now let me erase all of this work that I've done and maybe just say, you know, this thing right here is what we will be practicing in this section. Now, just to make some connections before we move on, one quick connection to the previous section where we had a warm-up. The point is that if you really do integrate f of x comma y comma z being just the constant function 1, output's always 1, so that's the function you have here, then you really do get, the area of the parameterized surface. And I hope you can already see that really works out, because this f of r of u comma v, if you compose, this is just trying to say that you've got to replace all the x, y, z's with whatever the parameterization is, but it's not going to matter in the composition if the outside function just always outputs 1. This entire part would just, if you had really just a function, constant function f is just always outputting 1, then even in a composition, this outputs 1. So this thing you circled here is just going to simplify to 1 anyway, and actually then we end up recovering on the right side over here, we recover the integral that we talked about right at the beginning up here anyway. Okay, so this really works, right? The point is that what we are about to implement and practice right here, in a special case when you integrate the function 1, would give you back the area. It's just now we need to talk about integrating things that are not just the function 1. Now we're going to talk about integrating any function, even if it's not the constant function 1.